Okay, when we talk muscle and nervous tissue, there's a couple of things they have in common and obviously big differences, okay? So, first and foremost, muscle tissue really well vascularized because of its energy use, okay? It uses a lot of energy, okay? It's a highly energy demanding, energy consuming tissue. It has these four major characteristics: elasticity, extensibility, contractility. Okay, when we talk contractility, we're talking a forcible shortening. Okay, it does it with force, with power. That's what produces movement. Extensibility, elasticity, we tend to associate these as a single property, and they're not. Notice that extensibility is that ability to stretch that we associate with rubber band. The elasticity actually is the recoil, okay, that return to shape. So it can be distorted, stretched, but then it returns back to its original shape. Now, excitability and irritability, this is the property that both muscle tissue and nervous tissue have in common: the ability to respond to a stimuli. Now, keep in mind, the stimuli is always chemical in nature. We'll go into that with greater detail when we go into both the nervous system and the muscular system. Now, the types of muscle tissue are based on location or tissue that it's connected to. So skeletal muscle, the skeleton; cardiac muscle, the heart; smooth muscle. Smooth muscle is virtually everywhere. You find it in all the hollow organs. It has, again, because of its anatomy, it has a very unique contractility, a very unique forcible shortening. We call this, oh shoot, uh, peristalsis, where you have this kind of wave. It elongates and tightens and does all these sorts of things. So it's kind of this wave motion of contraction. If you swallow in the mirror, you can see the bolus as it moves down your throat. That is in essence what peristalsis is kind of doing. Peristalsis is what allows that to happen. All right, so muscle tissue. When we talk skeletal, one of the things you want to pick up on is look at these striations. You can see these very predominant dark light bands. They're very, very close together. That is due to the arrangement of the proteins. Again, we'll go into that in greater detail. For now, you just want to notice this very dominating feature, that dark light band. Now, the other thing that you can see in this one is you can see the number of nuclei. So there's a lot of nuclei. One of the things to remember is when you see the formation of muscle tissue, especially skeletal muscle tissue, what happens is we have a bunch of individual cells. So I have this individual cell, it's got its nuclei. I've got this cell, it's got its nuclei. And then what happens is they fuse together, and now I have one long cell with multiple nuclei. And that's what's going on when we talk about the formation. Again, you can see the banding very predominant here. And that's one of those key points that you want to pick up on when you're looking at skeletal muscle. Now, cardiac muscle, you'll notice, also has striations. This diagram, you don't see it. The striations aren't as clean as they were with the skeletal. When you look at this one, you can see that very clean looking striations. Now, the other point is what this is pointing to here. Okay, right here. This is what's known as an intercalated disc. You can see a couple more here. You can see one here. Intercalated discs are real important. Right here, you can see it in this diagram. Intercalated discs are what join the individual cardiac muscle cells together. Now, what's important too is usually within these intercalated discs we find gap junctions. Now, one of those things you should remember from your review of Chapter 3 is gap junctions is one of the three types or means or ways that cells join with each other. You have desmosomes, you have tight junctions, you have gap junctions. Now, desmosomes and tight junctions we talked about with epithelial tissue. Okay? Gap junctions are literally that. You have our cell walls coming here, our cell membranes, and then I have this little gap, this little hole. The hole is important because it allows fluid or intercellular fluid and everything that's dissolved in that intercellular fluid to go back and forth between cells. So that means ions, concentrations can flow between. Gap junctions, in my mind, I always associate gap junctions with being able to synchronize activity. So it's real important that the heart be synchronized, or these contractions, remember it's a forcible contraction, that forcible contraction be synchronized so that you don't have one cell asynchronous to everything else. In fact, when one cell is asynchronous, that's what we associate with the fibrillations, the different types. You have brachycardia, different things like that. And so what happens is they have to, when they show those paddles on TV, most of the time in reality you have to get shocked with the paddle once to stop that fibrillation, to stop that brachycardia, and then you have to get shocked again to start up so that hopefully everything is in synchrony. Okay, now smooth muscle. Smooth muscle, as we said, lines the hollow organs. It's again involuntary because of the unique shape. Okay, it's what's known as spindle shaped. So it kind of has this point and a point here, and so because of that shape, it's when it contracts very differently. When you look at both cardiac muscle and skeletal muscle, it's very regular. There's no doubt how this is going to contract. These are going to contract in these directions, aren't they? Now, smooth muscle isn't. Smooth muscle doesn't have that same organization of proteins on in the interior of the cell, which gives smooth muscle a very unique. It can kind of contract this way. It can also contract this way, which is what leads to that very distinct movement that we associate with smooth muscle or hollow organ contraction. Now, we talked about early on, smooth muscle is often confused with what other tissue type? Now, hopefully you said dense connective tissue. Again, see how we have that real good striation? Okay, you can see the striation, you can see the cells and everything like that. Kind of similar to our smooth muscle, isn't it? But if you look carefully, we can kind of see how this seems to come. You can kind of make out a little bit of the points coming in. You can see how these are kind of meshed together. Now, the other interesting thing when we look at smooth muscle, okay, actually smooth muscle is often oriented in different directions. You'll see smooth muscle going the length of an organ, especially if we're talking a hollow organ. You'll also see smooth muscle coming perpendicular to it. So you're going to, and I can't draw perpendicular. Okay, so I have a sheet going this way, so I can see these cells kind of like this. If you go a cross section of a hollow organ, you actually see what looks like the ends of spaghetti. Okay, it's like you took spaghetti in your hand, chopped it in half, and looked at it, and you can see smooth muscle arranged this way. So it gives you a very different perspective based on that, whether it's a sagittal or a transverse type cut. All right, so now smooth muscle here, especially with this one, you can really see how you can see these points in there. You can see lots of cells and everything like that. That's probably the easiest way to differentiate this and the dense connective tissue. A lot more cells are in this tissue than what you would find in dense connective tissue. Okay, nervous tissue. Nervous tissue, like I said, we'll go into a lot of detail with nervous tissue when we go into the nervous system. For now, what you want to recognize is you can see these cells. Right here's a pretty much one. This one is actually what we'll get to talk about. We'll talk about them later. They're called glial cells, and glial cells are kind of like, they're not what we typically think of when we think of nervous cells, but they have a very specific function within the nervous system, and they are a type of nervous tissue cell. And as you can see here, support cells, different things like that. Again, nervous tissue we associate with the brain and spinal cord, but keep in mind, muscles had the ability to respond to stimuli. That means we also have nervous tissue within our muscles, because that's what provides the stimuli. Okay, so we also have it in virtually every tissue in our body or every organ, depending on what's going on, because we have to be able to control and maintain homeostasis. The nervous system is one of those primary controlling systems, therefore the tissue has to be very, very responsive and has to have that ability to send and receive information. And that's obviously the primary purpose of nervous tissue. And again, one of those key features, okay, is that ability that it's excitable and so can respond to stimuli. Okay, now a couple of points when you look at the tissue. Do not confuse this with reticular tissue. It's obviously very different. You know, you want to keep that in mind. There's a lot of different tissues you should be looking at. Look at spinal cord tissue, look at cerebellar tissue, look at cerebral tissue, look at some of the cross sections of the neurons and different things like that. Okay?